Welcome to the deep dive. We're talking to a very specific listener today.
Yes, we are.
You're a new marine engineering student, and right now you are probably staring down the barrel of a major, highly professional presentation.
A really intimidating one, yeah.
Oh, absolutely. But, I mean, you have the visual aesthetic completely locked in. You are going for these crisp, stark, white slide backgrounds.
Which is a great choice, by the way. Very clean.
Super clean. And on top of that, you've planned out these brilliant, vibrant, vector-style cartoon illustrations. You have this little vector marine engineer who is going to systematically point out the complex components of a ship's construction.
Visually, it is going to look stunning.
Right. But structurally, you are sitting there with this towering stack of dense source material. You're trying to figure out how to translate heavy engineering data into a script that won't just put your professors to sleep.
And that is exactly our mission today. We are going to act as your personal sounding board.
We are going to help you outline and script the narrative of your entire presentation, step by step, using your specific source material.
We're basically going to tear down that source material and rebuild it as a presentation narrative. The goal here is to help you project absolute confidence.
Because your professors are going to be scrutinizing your slides.
Oh, they are waiting for the Q&A portion of your lecture. They want to test your actual comprehension. So we want to ensure you understand not just what these massive steel structures are, but why they are engineered the way they are.
Right. Getting to the why.
Exactly. When you understand the underlying physical logic, you just become impervious to those curveball questions.
Before we get into the actual steel and welding, let's establish the non-negotiable foundation of your slide deck. The document you are synthesizing today is a text titled Ships Forward and Aft Construction.
Authored by Dr. Semeh Tawfik?
Yes, authored by Dr. Semeh Tawfik. Your very first move, before any vector graphics even appear, is to ensure Dr. Semeh Tawfik's name is front and center on your title slide.
That is crucial.
Your entire analysis, every single diagram you adapt, and every technical definition you provide is built entirely on his meticulous engineering work.
Giving proper upfront attribution sets a professional academic tone immediately.
Okay, let's unpack this. Translating complex marine architecture into an engaging visual lecture is a massive challenge, but it is also an opportunity to show off your grasp of the material. We should start your script right where the ship meets the water.
The front.
Your opening slide really needs to anchor the audience's focus. So you have your vector marine engineer standing at the front of the vessel.
Yeah.
Now, your audience of professors obviously knows what a bow is. However, as a presentation strategy, you want to show that you have mastered the source text by using its specific academic framing.
Right. Don't just say it's the front.
Exactly.
According to Dr. Semeh Tawfik's text, the bow is formally defined as the forward part of the hull of a ship. It is the point that is usually most forward when the vessel is actually underway.
Using that exact phrasing demonstrates rigor before you even dive into the heavy hydrodynamics.
It sets the baseline.
And following that formal definition, you need to state its overarching design purpose. The text makes it very clear. Bows are designed to enable the hull to pass efficiently through the water.
You are setting up a narrative about efficiency and resistance.
Now, to really grab the room, this is where you click to your next slide and transition from the sleek exterior to a cutaway view of the internal structure.
Ooh, yes.
And you need to use the exact labels from Dr. Semeh Tawfik's diagrams. But looking at these source diagrams, it is just a dizzying maze of intersecting lines and structural labels.
It really is. It looks like a solid block of ink in some places.
It does. You have the solid round stem bar at the very leading edge.
Yeah.
Behind that, you have breast hooks. There are panting stringers, complete with wash plates and panting beams spanning the space.
It's intense.
And looking at the side profile, the bottom is packed with deep floors, all leading up to the collision bulkhead, with various pillars supporting the deck girders above. It is completely overwhelming.
So as a presenter, how do you handle a diagram with that much sheer visual density without just reading a list of terms?
Right, you don't want to just read a grocery list.
You handle it by acknowledging the density as the core engineering feature. You don't need to read every single label aloud like a textbook index. Instead, have your vector engineer gesture to this dense network of steel and explain the overarching goal.
I love that.
This entire puzzle of stem sections, deep floors, and stringers serves a singular purpose, surviving the point of impact.
Because this is the part of the ship that takes the absolute worst beating from the ocean.
Exactly. By displaying the accurate labels from Dr. Tawfik's diagrams on your stark white backgrounds, you visually communicate the massive internal reinforcement required to push thousands of tons of steel through the water.
That is a much better way to script it. You let the vibrant graphic do the heavy lifting for the terminology, while your voiceover explains the engineering reality.
It keeps the momentum going.
Once you have established that internal reinforcement, you should transition your slide back to the exterior to highlight a very specific, somewhat strange-looking feature at the front of the ship.
The bulbous bow.
Yes, the bulbous bow. The text describes it simply as a protruding bulb at the bow or front of a ship just below the waterline.
What's fascinating here is the massive operational impact this specific structural choice has on the entire life cycle of the ship.
It's huge.
When you bring up the bulbous bow, you are pivoting your presentation from structural endurance to hydrodynamic theory.
Which professors love.
They do. The source text explains that the bulb modifies the way the water flows around the hull. This isn't just a minor design quirk. You need to emphasize to your professors that modifying this water flow achieves 3 critical benefits.
And the source text lays those 3 benefits out perfectly for a slide layout. You should have your vector engineer point to 3 bright, distinct bullet points.
And lay them out clearly.
Benefit 1, it increases speed. Benefit 2, it increases fuel efficiency. Benefit 3, it increases the stability of the vessel.
As a student, you really want to hit those 3 points hard.
Why is that?
Because they represent the commercial and practical reasons why marine engineers do what they do. We aren't just building floating boxes. We are trying to save fuel, move faster, and keep the cargo stable.
Delivering those 3 points clearly proves you understand the practical application of the architecture. So you have successfully navigated the forward construction section.
You demonstrated the internal complexity of the bow.
And you explained the external hydrodynamic purpose of the bulb. The logical next step for your presentation script is to take the audience on a walk from the front of the ship all the way to the back.
The transition slide here practically writes itself. Your vector engineer walks the length of the ship to tackle the aft end construction.
And looking at the diagrams Dr. Tawfik provides for the aft end, the engineering philosophy seems to flip completely.
It really does.
The bow was all about slicing through water and managing fluid dynamics. The aft end diagrams look like they are entirely dedicated to heavy mechanics, structural housing, and sheer brute force steering.
The diagrams reveal a completely different set of priorities. Your script needs to reflect that shift. You are moving from hydrodynamics to mechanical support.
So how do they map that out?
Well, when you recreate the aft end cutaway diagram for your slides, you need to map out a specific hierarchy of components. At the very bottom, providing the foundational shape, you have the stern frame.
Right?
Passing right through that area is the stern tube, which is absolutely critical for the ship's propulsion. Built up around that lower structure, you have the solid floors.
And moving vertically up the diagram, the complexity shifts. You hit the steering flat, and you can see the rudder trunk passing directly through it.
Yes.
You also need to make sure your illustration clearly maps out the after-peak tank and shows its relationship to the after-peak bulkhead located just in front of it.
Don't forget the vertical stiffeners on the upper deck.
Right, which the source labels as the poop deck and all the internal bulkheads. Again, it is a lot of terminology for one slide.
But the strategy here is similar to how you handled the bow. The overarching narrative for the aft end is extreme structural reinforcement to house-moving parts.
Look closely at the structural elements Dr. Tawfik highlights in this section.
You have deep centerline girders, centerline webs, and heavy brackets supporting the upper deck and the steering flat. You need to explain to your professors why all this extra steel is necessary.
Because this section has to house and support the crucial steering mechanisms of the ship.
Exactly. The torsional forces at play at the stern, where a massive rudder and propeller are constantly fighting the ocean, are immense.
Just a constant battle.
This aft end construction is heavily reinforced with solid floors and girders, specifically to withstand those dynamic forces while maintaining the watertight integrity of the hull.
I really like that framing. It elevates your script from merely describing a drawing to analyzing a dynamic physical environment.
It shows you understand the physics, not just the vocabulary.
So, your presentation has now covered the point of impact at the front and the mechanical powerhouse at the back. Now it is time to tackle the most narrative-driven section of Dr. Tawfik's text anchors arrangements.
This is a fun section.
For this section of your lecture, you should absolutely leverage your vector art style and create an animated slide. The text traces the physical journey of the ship's anchor chain, and your graphics should follow that exact path.
Starting high up in the open air and traveling deep into the dark interior of the hull.
An animated sequence perfectly matches the chronological flow of the hardware described in the source.
To begin the sequence, your vector engineer should be standing on the weather deck, pointing to the windlass.
The windlass.
The windlass is the primary mechanical winch. It is the starting point that actively pulls or releases the massive weight of the chain.
So the chain comes off the windlass, but then it faces an immediate physical obstacle. It has to somehow get through the solid steel hull to hang outside the ship.
And that brings your animation to a crucial component.
The hawse pipe. The text is very specific about this. It describes the hawse pipe as a heavy cast iron or steel pipe placed in the bows of a ship on each side of the stem. Its designated function is to guide the anchor chains from the deck level to outside the shell plating.
This is a moment in your presentation where you can demonstrate extreme attention to detail. Dr. Tawfik's diagrams don't just show a generic tube.
No, they don't.
They show the specific hardware used to integrate this pipe into the ship's structure. Your slides should highlight the specific castings used at the ends. Point out the casting at the forecastle deck, and ensure your vector illustration includes the wood sheathing positioned right next to it, exactly as noted in the diagram.
Oh, that wood sheathing detail is great.
Then, animate the path down the pipe, noting the weld, until you reach the casting at the shell side, right where it meets the local insert plate on the exterior side shell.
Those granular details are what will separate your presentation from a standard freshman overview. So the hawse pipe handles the chain going outside to the anchor. But what happens to the miles of heavy steel links when the anchor is pulled all the way up?
Good question.
Here's where it gets really interesting. The ship utilizes a second, entirely distinct pipe system to handle the storage.
Right.
While the hawse pipe directs the chain outside into the water, the chain coming off the back of the windlass goes down into something called the spurling pipe.
Making a clear distinction between these two pipes is vital for your script. Think of the spurling pipe as the indoor counterpart to the hawse pipe's outdoor function.
Indoor versus outdoor.
The text defines the spurling pipe as a pipe or tube through which an anchor chain passes to go inside, straight down below the deck of a ship. It is the funnel that leads the chain away from the elements of the weather deck and down into its designated storage area.
That storage area is the next major stop on your animated slide journey, the chain locker. Your vector marine engineer can point down to this compartment, which the diagrams show situated deep down in the forward architecture of the hull.
Drawing directly from the text, you will define the chain locker for your professors as a small compartment or space located directly under the windlass.
Meet inside.
Geographically within the ship, it is situated forward of the collision bulkhead and below the main deck. Its sole dedicated purpose is storing or securing the anchor chain cables.
And when you script this, remind your audience of the sheer physical reality of what is happening here.
Yes, this isn't a closet.
Not at all. It is a heavily reinforced metal room designed to catch and hold thousands of pounds of industrial steel chain dropping from the deck above.
The physics of that are incredible to visualize.
Which brings your presentation to its grand finale. The animated chain has pooled into the chain locker, but you have to address the ultimate worst-case scenario.
The scary part.
What happens to the very end of that chain? If the windlass fails or the anchor is dropped in water that is too deep and the chain runs out entirely, how do you prevent the entire system from just ripping out of the ship and sinking to the bottom of the ocean?
The source text addresses this with a fantastic engineering term.
The bitter end.
Yes.
What exactly does that term refer to in the context of Dr. Tawfik's text?
The text provides a very strict technical definition. The bitter end is the inboard end of a ship's anchoring cable. It is the absolute final link of the chain, the one piece that must permanently remain secured inside the vessel no matter what happens outside.
The mechanical arrangement of how this final link is secured is a perfect way to end your technical slides. You need to adapt the final diagram from Dr. Tawfik's text, zooming in extremely tight on this specific piece of hardware.
Zoom right in on the connection.
The text states that the bitter end is secured inside the chain locker by something called a clench pin. Your vector art should really highlight the intricate mechanics of this small but vital connection.
To conclude your lecture with authority, you should systematically list the exact hardware involved in the securement, exactly as it is drawn in the source diagram.
Break it down for them.
The structural foundation for this connection is the centerline bulkhead. Attached directly to that bulkhead, you will point out the doubling plate and a cope stiffener, which provide the localized reinforcement necessary for this high stress point.
Lots of reinforcement.
Extending out from that reinforced bulkhead are the welded lugs. The final link of the anchor chain is held by a shackle, and that shackle is secured directly between those welded lugs by the clinch pin itself.
That is highly detailed.
If we connect this to the bigger picture, your presentation will have just walked your professors through an incredible continuous chain of physical events.
Literally a chain of events.
You started with a massive steel anchor hanging off the exterior shell. You traced its massive chain up through the cast iron hawsepipe, over the mechanical windlass on the weather deck, down through the internal spurling pipe, pooling into the dark chain locker, and finally being definitively locked into the reinforced structure of the ship itself by this precise arrangement of welded lugs, a shackle, and a clench pin at the bitter end.
It is a brilliant narrative arc about controlling immense physical forces. So what does this all mean for you as you finalize your presentation? It means you have a highly structured, meticulously detailed script ready to go.
You're ready.
You are going to open by leveraging Dr. Tawfik's formal definitions to show academic rigor. You will explain the dense internal architecture of the bow and contrast it with the external hydrodynamic brilliance of the bulbous bow.
Making sure to highlight its benefits for speed, fuel efficiency, and stability.
Exactly. You will then pivot to the aft end, explaining how deep floors and centerline girders are required to house the massive forces of the steering mechanisms.
Showing that shift in engineering priority.
And you will bring the whole lecture home with an engaging, animated journey, tracing the anchor chain from the weather deck windlass through the distinct hawse and spurling pipes, all the way down to the ultimate security of the clench pin in the chain locker.
You have everything you need to deliver a flawless lecture.
Just remember, as you close out your presentation, to confidently display your final slide, crediting Dr. Sameh Tawfik. His document, Ship's Forward and Aft Construction, is the foundation that made all of these insights possible.
It is an incredibly thorough piece of engineering literature, and you are well equipped to present it. As you align your vector graphics and practice your timing, I want to leave you with one final thought to ponder.
This is good.
It might just be the exact type of curveball question a professor throws at you during the Q&A. We just discussed the massive weight of a ship's anchor and the thousands of pounds of steel chain passing through the heavy cast iron hawsepipe, over the windlass, and down the spurling pipe.
Right, tons of metal.
Imagine a catastrophic scenario where that chain is accidentally allowed to run out completely. Considering the sheer terrifying mass of the chain and the anchor free-falling through the ocean, how exactly does the ship's centerline bulkhead, even with its doubling plate and cope stiffener, manage to withstand the immense, concentrated physical forces acting on that single, solitary clinch pin during that final, ultimate pull?
That is exactly the kind of high-level physics question that separates a good student from a great engineer. Chew on the mechanics of that while you put the finishing touches on your script and your bright white slide deck. We are wishing you absolute success on your presentation.
You're going to do great.
You have the knowledge, you have the structure, and you are going to impress your professors. Thanks for diving into the source material with us, and we will catch you on the next deep dive.